this is also recording. Oh, nice. Okay. Multiple recordings. Hi guys. So I'm gonna get started here. Sorry again for being sick, I guess. I just keep like I was telling Yaakov, I'm like, I was healthy during the pandemic, and as soon as it seems like it's waning, I'm constantly sick. So it's kind of par for the course for me. Anyhow, so I'll try to keep going today until my voice gives out. Hopefully we can cover everything I wanted to cover. So I was, as usual, the semester is drawing to an end. I think we have 2 more lectures coming up, or 2 more weeks of lectures, and then we're done. So I wanted to make sure we focus today on figuring out what we're going to do for the presentation, and then how to give you guys the background for project 4. So I wanted to jump on the presentation first. So what I was thinking of doing was to give you guys till, I think you guys, your finals week is on is it on the 16th? Is that finals week for you guys?
Yes.
Yep. So I was thinking of giving you guys till Monday morning, the 23rd, to turn in both of those. So we're gonna make the due date. So if you guys, I don't know if it hopefully will helps you guys to have it after the finals. You can obviously turn it in before then. So due date would be so Monday, say noon on May 23rd. Okay, so on the presentation, I'm gonna first give you guys some background about, I've been looking for scaling issues, how do you scale, guidelines on how to scale. How can you guys try to estimate? So let me take a step back. So you guys took a chip and you were gonna try to figure out what to do with it to improve the performance, or what could be done to make it a better product, let's say. So, and it, as I think about more, this was the first semester I was doing a project, trying to think about doing a presentation like that. And I think it ends up being more difficult than I thought to do a real 360-degree job around what that improvement would be. So what I'm thinking of is making it sort of a simpler presentation. So we would only have 2 or 3 slides, and I'll talk to you guys about it sort of at the end of some of this information I'm going to give you guys, and sort of focus on cost of changing the chip, and then coming up with some justification about why we think a product like that cost difference would be worth it. So I'll talk about that a little bit. But first, I'm going to talk a little bit about scaling approaches. So, when you're, most of what you guys were thinking of, everybody was thinking of, was let's take this chip that's, I don't know, in some process, 40 nanometer, 90 nanometer process, whatever it was in, and going to a more advanced node. And that was, what would that do? I think that was on everybody's mind. That was a lot of the, that was what a lot of the sort of presentation plans we're thinking of doing. So I was looking for giving you guys some guidelines on what to assume about what to happen. And it's not a straightforward thing, especially in the more advanced processes. But so I thought I'd give you guys some background on how the scaling typically works. So there was when things were starting with VLSI or chip design, the big thing was the big economy of scale was how do you get more and more transistors into a chip that would roughly stay the same cost. And so, so basically there was this idea of very early on about scaling the process, so-called. So going from, was a scaling law. You guys, I hear about it in some podcasts, etc. It's called a Dennard scaling, or sometimes people call it classic scaling laws for CMOS. And this was the scaling laws that were worked till about early 2000s. And believe it or not, this concepts were introduced, the scaling idea was introduced around 1974 by this guy and his colleagues, Dennard and his colleagues. And if you guys want to think about it, it's kind of a roadmap for constantly improving on a CMOS process, so-called scaling. So what happens as you go from, so this is like a chart I found going through the years. The horizontal axis is the years, vertical axis is the feature size, and this is kind of basically looking at the process technology, kind of the same idea. So let's think about what was happening there. So let's first think about the MOS transistor. It's got source, drain, gate, and there's some doping concentration under the gate, and we need to hook up to it. Okay, so this is what the scaling parameters they came up with. So what they said is if we can kind of scale everything by this parameter K, roughly, from process to process. So let's say, for the sake of discussion, you were going to go from a 2-micron process, this is like being really old, to a 1-micron process. Okay, so K would be like 2 in this case because you're scaling from 2 to 1. So you're dividing everything by, so not dividing everything by 2, but your K factor would be 2. So for example, you would take your device dimensions, which would be the length of the transistor, you would divide it by a factor of 2, right, in that case. So it'd go from a 2-micron process to a 1-micron process. You would take the minimum width of your transistor would be in this kind of direction coming out of the board. You would divide that by a factor of 2. That would be the minimum size width. You would reduce your oxide thickness, which would be separation from the gate to the channel, by a factor of 2. So all your dimensions would shrink by a factor of 2 in this particular example. Now, when you do that, what else should you do? Well, you would have to increase the doping concentration. This is the number of acceptors. So this is, again, it's an NMOS. So you have an N plus source, N plus drain. So you need to increase the doping concentration in the channel by a factor of 2. So the doping concentration would have to get multiplied by 2. You would reduce your voltage by the same K factor. So let's, for the sake of discussion, say at 2 micron, your supply voltage was 5 volts. At 1 micron, your supply voltage would be 2.5 volts. And the reason for this is, one is you've reduced the thickness of your gate. So I want to make sure your electric field stays low enough that it doesn't damage the gate. And also because you want, because you're concerned about your power consumption, you're packing more devices into a particular device, you want to reduce that power consumption. Okay. And then the output current per transistor, you also divide it per unit width, I should say. So this is per unit width. It also goes down by a factor of K. Your capacitance goes down by a factor of K. And because of these factors, your delay time, when you combine all three, basically, if you think of your delay as being the voltage over current times the capacitance, you also, everything gets reduced by a factor of K. And so let me talk about that for a second. So if you guys remember, depending on how you model your circuit, so if you model our inverters by and a capacitor, that's what we're driving. So if you say you model it by a current, the N MOSFET, and you're pulling down this thing from a 1 to a 0. If you think about this as a current source driving a capacitor, you want to change this voltage by this delta V to go from logic 1 to a logic 0. That has to move by the supply voltage in your process. So that delta V, your delta V is going to be VDD. And you're going to have a certain current to do that with, and you have a certain capacitance. So if you think about the change in voltage, so when you look at dQ dt, which is I, is equal to C dV dt. So if you look at dt as the amount of time it takes to fall, like your fall time in this case, is equal to C dV over I. Okay, so this dV, as I'm calling this delta V, so is equal to C VDD over I. So this is kind of a proxy for your transistor delay, and that's where this comes from. Okay, capacitance times voltage over current. And then your power dissipation, because it's voltage times current, that's going down by the square law factor, which is good. So all that, because we reduced the dimensions by 1 over K, and we can kind of pack more devices. So think about this. If you reduce each dimension by a factor of K, okay, area-wise, for the same circuit, area is going to be sort of moved by 1 over K squared. So the area per transistor. Is going to change with 1 over K squared. Meaning that if you had a chip of a certain area, you could pack K squared more transistors in there. Okay, for the same, say, centimeter by centimeter area, because the area per transistor goes down by a factor of K squared, you can pack K squared more devices in there. So basically you can keep, because your power dissipation goes down by 1 over K squared, and you have K squared more devices in that's some area. So it's K squared more devices, more times power dissipation per circuit. So this would be 1 over k squared. So this stays constant. So basically, although you're putting in double the number of transistors, every time you scale, go in a process from 2 micron to 1 micron, then you go from 1 micron to half micron and so on. The power density, meaning how much power you burn up in the same square centimeter or square millimeter on your chip, stays constant. So this was and then, the wiring width and stuff like that kind of scales also with 1 over k. So this was the thinking of how do you make, go scale down in process and have something that doesn't blow up in terms of power consumption and actually, improves in performance. And you end up with something basically like this again. So it went from, they were planning on doing this sort of back in the 70s, and they followed this curve roughly, I guess depends on when you think about it, till like the late 90s or something like that. And so this is this classic so-called Dennard let's see, sharing screen. What do I do to get back? Guys with me? Sorry, I'm trying to figure out how to like not leave the meeting.
Yeah, we're still here.
What's that?
Dad, yeah, we're still here. You can try unsharing and resharing.
Yeah, I probably have to do that. So why stop due to those sharing? Okay. Screen. Okay, so basically was the so-called Dennard scaling. That was sort of defining how fast the process nodes were getting smaller and smaller. So you notice, for example, you're going from, I don't know, this is like maybe this is we didn't really have a 1, this might be a 1 point, let's see, what process would this have been? I think this might be a 2 micron process. This is probably a 1 micron process. Down here is like maybe a 0.13, something like that process. So this was what was happening. And then at some point, this stopped working, this whole idea. So it becomes, and this is kind of where we are, because typically the chips you're looking at, unless you're looking at a very old chip, we can't really use this classical modeling. Things that you're looking at mostly came out around this time frame. So, it's not so easy to look at something like this and say, okay, this is like a straightforward scaling factor. So that's, the problem I've been having with what to tell you guys in terms of what to do with your presentations in terms of where do things go. So the reason why things, by the way, and I'm just, so let's talk about why this failed, right? So, or stopped working. This simplified, straightforward level of scaling failed because at some point, the oxide thickness of the transistors got too thin, and that was roughly around the 1.2 nanometer process. That's meaning that if you have a gate and you had, your oxide is sitting here. So the oxide is sitting here. This just got too thin. And what would happen is you would get carriers channeling straight through this dielectric into your gate. So gate leakage became too big of a problem to just go ahead and scale like this. So the industry needed to do something else to get the performance improvement with time, because that's where the whole business model of the industry was based on every couple of years getting a significant reduction in overall chip cost, or transistor cost, I should say, and an improvement in performance. So there were like 3 technologies that the industry is, like 3 big technologies. There's like thousands and thousands of things that the industry is doing, improving on. But these were the 3 big things that improved the situation. So starting in sort of the 90 nanometer process and the 90 and the 65 nanometer processes, what they did was to, without really changing the gate. So why is it important to change the gate oxide? It's important to change the gate oxide because as your voltages shrink, you lose control over your channel. So so the electric field that you get from, so the electric field you get from the sort of the gate to channel is your voltage on your gate divided by the oxide thickness. Okay, so it's kind of like just a definition of electric field versus potential. Okay, so as if you keep reducing the voltage every generation, if you don't also reduce your oxide thickness, your electric field goes down. So this is your controlling electric field, which means that you just can't turn off the channel anymore or turn it on very strong. So if you were like sort of keeping this thing, you have to keep, every time you reduce your voltage, you'd have to reduce your oxide thickness to be able to keep your output current and then be able to turn off the transistor. And remember that your output current is roughly the mobility of, let's say for NMOS transistors, is the mobility times W over L times the oxide capacitance times, you know, your supply voltage, etc. So this mobility has like a big effect on the current. So this would be the mobility of electrons in the case of NMOS. In the case of PMOS, the important parameter would be the mobility of the holes. So the first innovation was basically improving mobility. So increasing, this was increasing current at lower electric field. So you wouldn't have to reduce oxide thickness. So what they did was they actually changed the mobility of the electrons and holes. So this strained silicon is change electron and hole mobility by change, let's say, increase is the right word to use. Without what's the word I'm looking for? So without increasing doping concentration. Or reducing, I guess, without changing, let's say without changing doping concentration. And the idea was this thing that you hear about, it's called strained silicon, which is actually, they've been continuing to use that. So that's a technology that they started at that node, at the 90 nanometer node, and they continue to use. And what the idea behind it is, you can improve the mobility of electrons and holes by putting actual physical stress on the silicon. So what they do is they put sort of, I guess it's called tensile force. So that's when, so for electrons, so that's tensile strain. And they do that by depositing a layer of silicon nitride above the channel. And that tends to put this has a different sort of, I guess I'm not really a mechanical engineering person, but it puts a separation stress on the channel. So this is for the N MOSFETs. You want to sort of separate, put some strain on the silicon in the channel, and that's a separating strain. So you want to have, if this is a channel, you're actually putting in a strain that is pulling sort of the channel apart. Of course, it doesn't really pull the channel apart, but it just puts enough of a strain there that that increases electron mobility. And I'm not sure why a tensile strength strain increases electron mobility. I mean, I'd have to kind of look back on it, but that's what it does. And the other thing I'm not sure about is why, when you're looking at holes, you want to create compressive strain. That improves the hole mobility. And the idea there is for, if you have, that's for, so that's, and this is NMOS, this is PMOS. And it's the kind of strain that goes in this direction. And they did that by doping the source and drain for the PMOS with germanium. And that creates this compressive sort of tension or strain. And between these two, they managed to get significant improvements in mobility in the 90 and the 65 nanometer nodes. Okay, so that by itself, although they continue to use that to this day, at some point that also stopped giving significant improvements. So the next step they went is so-called high K metal gates. So instead of using silicon dioxide in the gate, the idea was to replace that with higher epsilon material. And so what that does is, if you have a higher dielectric constant, you're basically, again, without increasing your thickness, you can get a better control of the channel with a higher dielectric constant material. And they started using that. So this is the reason I'm mentioning this, is if you look at like sort of marketing literature on the chips you're looking at, et cetera, it might mention strained silicon and might, when it's talking about the process, it might talk about how high K dielectric process. And then lastly, this last technology that was very big, starting in the 22 nanometer node and below, is something called a FinFET, which again, you guys, like, you might have seen it in the brochures for the chips you're looking at, boasting that they have a FinFET technology. And the idea behind the FinFET is kind of hard to describe, but basically what happens is, instead of, sort of a classical chip up to that point, the source and the drain are inside the silicon. Okay, it's on the gate is sitting on the surface of the silicon above the channel. And so it's trying to control, so this is this high K dielectric gate. So the gate is trying to control this channel with the electric field on it. And so what they do is they actually etch the silicon away. So it basically, the gate wraps around the channel. So basically, not only do you have, sort of classically, this would be the gate on the top here, but instead of it just being there, it's also around here and around the other side of the source and drain. So basically what they do is they etch, instead of having, I guess it kind of looks like a fin. That's why they call it the FinFET. I guess this thing looks like a fin to some people. And so you basically have your transistors end up having sort of this. So if you can kind of look at it, this might be in this SEM, this might be the source and drain, and this is the gate. But you can see that sort of this waffle pattern because they're etched down. And the idea is that, again, that the gate is wrapping around your channel to have more, for the same sort of electric field, you want to have more control over your transistor switch. So I guess if we can see a pattern here, the idea is that you want to basically, with the same electric field, or by kind of trying to reduce the electric field, you want to somehow keep your control over the channel the same. And so all these things, one way or another, all these approaches have to do with trying to get more out of the same electric field, or try to reduce the electric field and therefore reduce the supply voltage and get the same transistor performance. So that's kind of what's going on with these innovations, which are great for the industry. But as far as our presentation goes, these things don't have like a sort of a straightforward table like this that we can use for our scaling. So the best I could find was kind of charts like this, where this is from Intel. And they're showing that, as the process technologies scale, so all this stuff is going from 45 nanometer down. And again, these are processes where sort of the classical scaling stopped working, and these kind of technologies started to take over for scaling. So there, you basically are in a situation where you are getting improvements in costs and so on, like in this particular case costs, but it's sort of less predictable. So by predictable, I mean here, if you notice, there's log scales, and they don't give, these being private companies, they're not giving us exact dollar amounts, just giving us relative scales, okay? So a straight line on a log scale would be sort of an exponential improvement. So this kind of tells us that square per transistor, so this is not, this is, let's see what happens here, is you're getting sort of lower, your transistors are shrinking faster, I guess, that's what that means, than sort of exponentially. So you are getting a shrink better than exponential in your transistor sizes. Your wafer prices are going up. So the dollar amount per millimeter squared for the wafers are going up. And I think we have some tables I think I passed out in terms of the wafer price with different processes that show that. And then overall price per transistor is going down. Okay, but it doesn't quite tell us how much. So, but at least we have some other data points for it. So I'll come back to that in a bit. And then this is from the same source. This is from Intel talking about their processes going from sort of 32 nanometer to 10 nanometer. And they got transistor performance, capacitance, and performance per watt. So sort of, I guess that's, power consumption and performance scaling. And all these things are improving sort of on an exponential basis, sometimes not quite, but getting reductions in basically power consumption and improvements in performance. So I guess you can kind of say that's what you would almost kind of expect to get in terms of power consumption and performance with scaling. So that's like the best I could come up with. So which leaves us with this difficulty on what to do on the presentation. By the way, any questions so far about all that? So I know it's pretty qualitative, but the main thing I wanted you guys to get is about why, going about why now, as we're talking about these more advanced processes, it's kind of hard to tell where things are going. I mean, where like how much, it's hard to come up with like a simple equations about what to expect. So we're going to have to make kind of a bunch of like assumptions and try to be qualitative. All right, so this is what I was thinking we could use as the format for our presentation. So basically sort of a much simpler presentation than what I was thinking. And just basically 2 slides. Okay, you could make it maybe 3. So slide 2, maybe slide 3, but I try to keep it less than 3 slides. Okay, the first slide focusing on cost. Second slide sort of focusing on the business case, and maybe a third slide with that as well. So I thought I'd give you guys sort of an example of what I mean by that. So one of you guys, I think it was Rachel, a while back, she sent me I think this is the chip. Rachel, is this the chip you're working on?
Yes, it is.
Okay, so it was a while back, and I have been sort of mulling over what to do with this. So I looked at this as like as a test case to try to figure out what this looks like. So I'm gonna try to give you guys like an example of what a presentation would look like, something like this. So looked at this and basically doesn't give us a whole lot of Let me see if you guys can't see my the cursor here. I guess kind of I'm going to try to zoom in just with my hand. As you can see, basically it's talking about this being a 14 nanometer FinFET process. Okay, so that was kind of one of the clues I had looking at this thing. Then I started looking at it, and it mentions that it's a, they call it a Zen chip architecture. Okay, so then I went to the solids. I think I mentioned to you guys the IEEE journal, and I looked for the Zen microprocessor, and fortunately they had a paper on it. Okay, kind of talks about it in more detail. In fact, in quite a bit of detail. It again mentions, you guys can't see mine, but I'm just sort of zooming in on the FinFET here. So it mentions that it's a FinFET process. There's quite a bit on the architecture here, but I figured you guys aren't gonna, not everybody's gonna be able to get this level of detail about the chip you guys have selected. So I thought I'd simplify it and just go with the 14 nanometer process and do some sort of quick calculations. Okay, so let me see. Look at my calcs. So, so the first slide would be, whoops, let me do it. Make it a, that's good. Okay, so first slide would be, let's say I'm Rachel doing this now, would be cost. So basically I would start with some existing, and there's no, for this presentation, there's no right or wrong, I guess, because we have to estimate a bunch of stuff, as we mentioned before. So in terms of the cost, it's okay with an existing cost. And I want to say that was $200. Does that sound about right, Rachel? Do you remember what the cost was for this thing that you guys were asking?
Professor, I think you were stuck for a while, for like a minute or two.
Guys, can you hear me still?
Yes.
Yeah, you just cut out for like maybe like a minute.
Yeah.
Guys, can you hear me?
Yes.
What is going on? Guys, can I get a sound check?
Hello.
I can't hear. We can hear, but you were frozen for a minute. I can't hear you. Okay, I guess as long as you guys can hear me. I can't hear you guys for whatever reason. I'm not sure why. External network. Guys, can somebody say something again?
Hello.
Great. Thanks, guys. Now I can hear you guys. Sorry. I'm not sharing the screen either. Let's see what happened. Okay, so yeah, I was trying to come up with some cost. I was asking, I think I was asking Rachel if $200 was roughly right.
That's about
Then-
right.
That's, so let's say it was sort of, this is assumption. So you would say, you know, based on pricing at I don't know, Arrow Electronics or DigiKey or something, wherever you got it from. Okay, now you have to assume what this is existing price. So what you can buy it for. So you got to figure out what is the existing cost to the manufacturer. This was AMD. So the relationship between the price and the cost comes down to something called the gross margin. And, you know, I think we talked about this going back, but basically that's the difference between what it costs you and what it costs to make. So I looked up on the internet and, you know, I was kind of, what was it? I don't know, you don't need to really look this up too much, but looked at the AMD sort of gross margin is like in the 50% range is what it says. Okay, and that's what I was kind of estimating also, so it's not a big surprise. So that's ends up being about a 50% gross margin. So that means that the existing cost would be around $100. Okay, so roughly the equation is cost over gross margin equals to the price. So, okay, $100, then we know that, hope I'm still with you guys. So we know that this cost has got three components. So it's got, you know, we got the silicon cost, it's got the package cost, and it's got the test cost. So you're going to have to assume something for the package. It's sort of a high performance package. So you could assume this is, you know, $20 to $30, something like that. And you can assume the test is something like $20. Again, these are a lot of assumptions you're going to have to make. So I assumed, for example, a 10-minute test at $20 per hour. So if this is 20 bucks, this is 20 bucks, that means their silicon cost was like $60, something like that. So what would that mean? That's basically, I'm going to assume a wafer price. So at 14 nanometers of $5,000. So assuming that it cost them 60 bucks for the silicon, that gives me a number of die per wafer of about 100. Then it comes out to 104 die per wafer. Which I can kind of try to double check with a, can you guys see the gross die per wafer calculation? I basically started trying to figure out what die size this thing was. And I just was trying to find something that would give me like roughly 100 die per wafer. So I was kept putting in numbers here, started off with like 10 millimeters on a side. That gave me 577. So that was, I could tell my die size was too small. So I basically just progressively kept increasing my die size till I got something like what I was looking for. So 112. And that's it's assuming a fab yield of 62%, which is low, but it's not sort of unheard of. So that all that makes sense. So it's this gives me like a yield of 64%. You guys see how I came up with this silicon cost? And like the number of die per wafer?
Yeah, it's clear.
Okay, so basically now what you can do is you can say, okay, well, if I go from a 14 nanometer process to a 10 nanometer process, say, what happens? So you know, you have some idea about how much your die will shrink. Okay, going from this size to this size, how many more transistors you can get. Sort of like actually in reverse. So let's say you got the same number of transistors, say it's whatever it was in this same product. So we were holding the number of transistors constant. And we're saying, okay, we're going from 14 nanometers to 10 nanometers. So we're going to get, I don't know, like, let's say we get 150. So, whoops. So instead of 104 die per wafer, we get 150 die per wafer. And our wafer price goes up by 2 something, like maybe it's $6,000. I don't know what the assumptions were. Okay, so let's say all that gives you is the silicon cost. So that tells you that the silicon cost at 10 nanometers is going to be $30 when you make that port. Okay, so you had your silicon price at 14 nanometers was $60. Let's say at 10 nanometer, I'm just using examples here, $30. Okay, so you haven't changed, assuming you're doing everything else the same. So package cost doesn't change. And you're still testing something of the same complexity. So test cost doesn't change. So basically those dollar amounts start being the same. So the total cost at 10 nanometer ends up being, $30 plus 20 plus 20, which gives it makes it $70. So that's your total cost at the new node when you did the shift over. Now, okay, now you're going to have to think about how many justify. Again, this is like something, there's no right or wrong answer. Kind of think about what the product is, how many you might be able to sell, justify it somehow. You're going to have to think about like why you would think such a thing. But let's say you assume that you sell X number of the new parts. So let's say you sell 1 million. Let's say 10 million, actually. 1 million won't make any sense. 10 million of the new parts. Why do you think that? Well, it's made for PC products. So, PC volumes run into the millions per year. Okay, so if the product line is like a couple of years, makes sense that you might sell 10 million or so. Okay, so there you have 10 million parts times $30. Let's see, times, let's say you sell it for the same, so you're selling it for the same margin, or sorry, you want to sell it for the same price. Let's say your price is $200. Now you're making $130 per part. So that's times 130. Okay, so that ends up being 1.3, is that $1.3 billion? Seems like a lot. Did I do that right? Maybe I'm assuming too much of a number. So let's say it's 1 million parts you sell. So that's $130 million. You make over this product. So this is the money you would make from this selling this new product. And the money you would have made if you'd stuck with this old product would have been $100 million. So the delta in dollars is going to be $30 million. So now you got to figure out, does it make sense to spend that money so what performance power improvement you expect to justify the customer interest? So I said this kind of badly. Let me put it to you another way. Let me do it another way here. So, so another way to look at this is if you, let's say it costs you guys, so it's not going to cost $30 million to make a new chip. It's going to cost something like $130 million, right? So let's say it costs you cost to develop new chip is 130 million. So the question is, what type of performance improvement would you expect to sell enough parts to justify it? Change. I'm not sure that made sense. Can you guys follow me with that? What I'm saying there?
Yeah, I believe so.
Okay, so basically you're like looking at, I think the costs are straightforward. Then where it gets kind of fuzzy, where you guys have to kind of make a business case, is figuring out, are these dollar amounts, do they add up to whatever, either you can sell more parts or you can make more margin for the number of parts you sell. And like what that means, either like the performance stays the same, or maybe you can argue that you can charge more for the part. So you're going to have to basically play around to figure out why you might be able to justify it. Okay, so what I'd like to do for the presentation is have you guys take some shots at this, and then I'm going to have basically slots. Maybe we just have like, let's say we have 20. We have, what's the best way to do this, guys? I think we're going to have roughly 20 teams. So let's say what I was thinking of is next Friday, if I have sort of individual sessions with 10 teams, that'll give us, our class is about 3 hours. So I think we could have about 20 minutes per team. That is all adding up to discuss what you guys have come up with. And we can kind of like work on it together. So the idea would be, so on Friday, Friday, May 6th, I would meet up with 10 of the groups. So I would open up reservations for you guys to sign up for, time slots there. And on Friday, May 13th, I would be sort of talking with another 10 of you guys. Does that work? So instead of our classes, we'd have the individual meeting to go over the presentations.
So next Friday that's not like the day you grade us, the day you're kind of prepping us.
Yeah, and then you would be turning in your final presentations on the 23rd. So you'd have till then for us to sort of sort together for the prep. Yeah.
Got it.
What are we
Okay.
turning in then? Just slides, or are we doing a video?
Just either 2 or 3 slides, basically.
So also we're not gonna end up actually presenting in class.
Yeah, I think we're gonna run out of time to present. Yeah, so it'd be 2 or 3 slides for the whole presentation. So the presentation is going to be pretty simple. I mean, it won't be simple, but it'd be very brief. So basically 1 slide on cost. So you would be going through roughly like what I'm doing here, where you're trying to estimate the cost of what it takes to make the part and what you would sort of the difference between the cost of what it makes to what it is now and what it is with the new product, the way you guys are thinking about scaling it to a smaller process. And then the second slide is basically, justifying why we think that might be, what the numbers would look like and what performance improvements and why would anybody pay for that difference. So for your presentations, I would come up with your estimates on what the costs would be and the cost of moving to a new process, whatever process you have in mind. Again, that's sort of your calculations for doing that. Does that make sense?
Can you say it one more time?
So let me write down what I'm saying here. So May 6th and 13th, we would be review your slides. Okay, so for that, we'd need your cost estimate for existing product. So including justifications, right? You're gonna including assumptions. And then we would need to make a cost estimate for new product. Say a new process. Again, include assumptions. And those assumptions could be, well, I think I can get to the chip will shrink by this much. The wafer price goes up by that much, and the yield changes by this much. So, and can I go? The package price doesn't change, or the test time doesn't change. So those are the assumptions. Okay, so basically those two cost assumptions, and then sales volume assumptions. Do you think you're going to sell, 100,000 of these? Do you think you're going to sell 1 million of these, etc.? And then we're going to have to work together in our sort of time increments to come up with some why this would be worthwhile doing.
Professor.
Yeah.
So we're basically meeting up with you to kind of brainstorm the thought process and the calculating the costs and etc. instead of presenting.
Yeah. So basically, in the May 6th and 13th, we're going to be reviewing, instead of you guys presenting, you guys would come in your, I guess you'd have your first slide made. Does that make sense? So come in with slide 1 with this information, with whatever you guys have been able to figure out. Is that part clear? Like what I did?
Yeah.
So again, you're going to have to make lots of guesses, lots of estimations. I'm more looking at, are you guys have the, following a thought process, and, did you consider all of these things? There's not that many factors. And then I think together, we're going to come up with ideas on slide 2, which is, what are we going to do with that? Like, are we going to try to sell more product to make this make more sense? Are we going to try to shrink the part more? Are we going to go to, a different, better functionality? how do we justify the cost of making this thing? What is to come up with what is our guess for development cost? Okay, so that's the part I'm going to go over with you guys. The problem is, I think you guys are going to have a hard time coming. This gets like a very complicated. So for example, let me give you guys an example. Let's say you had a part that was a 65 nanometer part that you said, I'm going to scale this to a 45 nanometer part. So that's the old process. This is the new process. Okay. This is going to be much lower development cost than if you had a 28 nanometer part and you were moving to a 14 nanometer process. More development cost. And during our time together, I can talk to you guys about that and why one is more than the other and sort of talking through it. But it'd be very difficult for you guys to come up with estimation of development costs. And, like sort of, I think you need lots of help in terms of like the business ideas, etc. Whereas like the cost, I think you have enough tools to come up with some guesses as to here. I think we'd have to work together to come up with this for your second slide. And I'd be basically working with you guys, like you said, brainstorming, coming up with ideas, and then you're probably going to have to go back and think through, maybe come up with some ideas here for your final presentation. Does that make sense?
Yes, it does.
Okay, so guys, I know this is pretty fuzzy. And like I think I told you at the beginning of the class, I'm like, the presentation is like something I was like as an experiment, but I think the lesson I've learned is that it might be a little too difficult for this one class. Like basically if you were on class 2 or 3 of our, if it was a multi-class series where you guys had more experience, we could dig into it more. So I'm not looking for, like, don't get too stressed out about it being fuzzy. I realize that it's a fuzzy question. I'm really looking mostly for your thoughts, the way you're thinking about what could happen. Did you guys sort of absorb the sort of high level lessons of the class about what happens with performance, power consumption, cost with scaling? So hopefully that makes sense. Yeah.
Professor, just a quick question. So basically that's like a combination, like we're basically shrinking down all the slides into those 3 basically as a summary.
Yeah, so basically the whole thing is going to be 2-3 slides.
Got it.
That makes sense?
Yeah.
And so also, when you're doing a pitch, like a business case pitch like this to upper management, a lot of times you only had to have a few slides to make your point. So, they're not going to sit through probably like 30 slides or something like that. So it's good to be able to also shrink the number of slides to just a few facts and see if it makes sense, and they'll give you a thumbs up or thumbs down about how to proceed.
Sounds good.
So I'll make, I think there's 20, if I'm correct, I think we've got roughly 20 teams. So again, so we'll have 3 hours, that's 180 minutes. So it'll be about 20 minutes per team. So I think we should be able to dig in pretty well. And if we run out of time, I'll just make some additional time. If you guys, we can sort of meet together afterwards to tune things a little bit better. Any other questions, guys? Yeah, I'm gonna try to make the meetings in person. We can also try to make it, well, either we'd have to make a decision to do it in person or in Zoom. Is there a preference for you guys?
Probably personally Zoom. Because it's a Friday class.
Yeah, so you'd prefer Zoom, you said?
Yes, please.
Okay. So Eric would like it in person. You know what? I should be able to do, I guess I can put Zoom in the classroom. So what I'll do is I'll count on being on campus. And then you guys, we can either do a Zoom or in person, depending on your preference. So I'll put a little chart there and ask you guys if each team, whether they like it in person or Zoom.
Professor,
Yeah,
will we be meeting at all on like the actual like day of finals week?
I wasn't planning on it, no.
Okay, thank you.
Yeah. We don't have a final. Basically, we have 4 projects, so you have one more project left, and then the presentation. Any other questions, guys?
Yeah, I guess these time slots, are you, did you say you're sending something out for us?
Yeah,
to,
what
like,
I'll do
pick,
is
or are you gonna pick for us?
I will put up. Yeah, I gotta figure out the best way to do that. I guess I would just pick for you guys. I think that'd be the easiest thing. You guys can send me an email if you have a preference, or we can move things around. But it would basically be during the class time. The regularly scheduled class time. Any other questions? Let's go. We can choose to go in person or Zoom. That's right, Kathy. So we can do it either in person or Zoom. Any other questions, guys? Okay, so let me move on to the next thing, which is project 4. Let's see, where should I put that in? So let me first describe project 4. I'm gonna have this in written form, like our normal project form, but I want to just sort of give you guys some background. because then I'm gonna kind of give you guys a little bit of a lecture on some of the things you need to know to be able to do this project. So what we did for, project 1 through project 3 was to use basically the concept of the clock buffer to look at a few different things. So for example, we started off with, project 1 was just the CMOS inverter, sort of basic operation. Project 2 was power consumption for buffer. Project 3 was delay, speed, and interconnect. So these are all things that are internal to the chip. So when you look at a chip, you think about the silicon chip sitting here. Again, the clock, your clock buffer is sitting here. And it's basically providing a clock to things near and far on the chip. And it has a certain power consumption. It can do things at a certain speed and so on. And so, okay, so this is all stuff that's happening in the chip. But the chip is actually part of a bigger system. So the chip is sitting in a package. And that's what you see when you buy a chip. Okay, so this package, we're going to talk a little bit about this package. This thing has wire bonds that go from the chip to the package. And then the package has, it has pins, or for ball grid arrays, it has balls. So those guys are things you would have seen, packages you would have seen. If you look at a microprocessor or something like that, it looks like something like this with connections, and that's sitting on your printed circuit board. So this means that as far as your clock buffer is concerned, it's also sitting in this environment, really. And so what does it mean to it? Well, the main thing for a clock buffer is that it's getting its power and ground from these wire bonds. So these wire bonds, as we'll see, have something. A wire bond has an inductance. And we need to basically simulate or model this to really accurately model how well something like this will work. Okay. Second thing is that this signal is coming in from the outside. Sort of bulges. So this clock signal is coming in from the outside, and that outside entity has to be able to drive our buffer. So you can think of, I've got a big capacitance on the chip. So you guys had these loads. That we were driving on chip for your project. And so to be able to drive those at the right speed, you guys got to make these as wide as you could, as you wanted to. Okay, but in reality, something else has to be able to, or has to be able to drive. Something is driving this guy. So this guy itself, you don't have the freedom in reality to make this as wide as you want. Or I guess you can make it as wide as you want, but there's a penalty associated with it. So basically the gate capacitance here is the gate capacitance for your NMOS and the gate capacitance for your PMOS. And so if I take each one of these, it's the width times length of your NMOS times the capacitance Cox. This is capacitance per unit area. This is gate capacitance per unit area. It's equal to that, and this one's your PMOS. So this is your N, Ln, WP times LP times Cox. So as we make this thing, as we make these wide to drive this load, you can see it's directly proportional. Its loading, the loading of this buffer itself is proportional to the width of these transistors themselves. So the previous stage now still has to be able to drive this. So you can see that, and then, this might need to be big to drive this. And so something else would need to be able to drive this, et cetera. So we're going to have to look at how do we drive a big stage? What's the most efficient way of driving something like this? Because there's no way in this particular case, there's no way around needing to make this large devices, because it's driving a big load. It needs to source a big current. So there's no way around making this guy large. And so we got to figure out how to drive it. So we're going to look at that as well. Okay, so let's first look at the first part about this, which has to do with what the part sits in. Okay, so basically, I don't think we talked about packaging before. Did we talk about this previously? Do you have any memory of me talking about packaging?
Yeah, briefly in the beginning of the semester.
Okay, so maybe I talked a little bit, and then I'm going to sort of dig into it a little bit more. I think we talked about this in the context of your presentation about the different types of packages that are available. But so they're big packages, they're small packages, mostly having to do with two factors. So in all cases, the chip itself is not typically what sets the limit to the package size. It is the number of pins and the power consumption. So a way to look at the packaging of silicon chips is, everything on the silicon chip is, so on chip, things are sort of micrometer size. So things are very, very tiny on chip. At some point, we're going to have to make the connection. So on a PCB is printed circuit board. Or essentially anything outside the chip, you're looking at sort of millimeter sizes. So these are really a rough size, right? So, it's not exactly a millimeter, it might be, stuff that you can see, like you can actually take a package and look at these pins and you can see the pins. So you can see the separation between them as 0.5 millimeter or a millimeter, the size of these pins or these balls. It's stuff that your eye can see. So it's in the millimeters, the package itself is physically big, etc. So you need to, if you look at the routing on a printed circuit board, if you actually take a printed circuit board, look at it, you can make out the individual connections on that printed circuit board. Again, meaning that they're physically large. So you need to have some interface between your tiny chip with all these, everything being really small, and these bigger sizes. So you can think of this package as something that basically lets your chip interface with this sort of a physically much more imposing things that it's sitting in. Okay, so the pins on a package again they're sitting on, maybe not on exactly a millimeter pitch, but something like that. They're rather large. And so that's kind of what sets the size of the packages, because the printed circuit board manufacturers, they can't live with something very, very small. They need something this big to be able to work with it, to be able to put it on a printed circuit board, to interface it with the rest of the printed circuit board routes, etc. So that sets the size of these packages, but basically the connectivity from the chip to the package is really usually the same. Okay, that basically you're looking at basically different ways to sort of bond from the chip to the package. So you have a couple of things. So this is like a really simple package. And this is kind of the chip sitting in there. So the chip is sitting like this inside your package. So how can I best? This is like a pour. I'm going to draw kind of package three. Maybe I'll try to draw 3 sides to the package instead of leaving the front. So it's look like, boy. This is really a poor drawing, so I apologize. But basically, this red thing is your silicon chip. And it's not to scale. So it's sitting here inside your package. There's a opening in the package where this chip is sitting in. And then this chip typically has a bunch of so-called pads, which are openings in the oxide of the chip. So a pad looks like something like this. This is, metal, last metal. So it might be, depending on your process, it might be metal 8, metal 9, whatever it is. And then if you wanted something connected to the outside, you basically route it to there. And then, so this is maybe, 80 to 100 micron. This is pad. And what they do is they bring in try to draw it, is a wire bond. So there's a pad here, and there's a tool that basically physically goes in. It looks like, needle, you can kind of see it. It bonds, basically it puts a gold bond between a wire bond. So it basically deposits a gold wire. Typically it's a gold wire. between a pad on a chip and a pad on the package. And then that this package, basically, there's connectivity inside the package that routes these different pads to different pins. So you have kind of a couple of things going on here. One of them is that the number of connections to the outside. So let me put two things, is the number of transistors on the chip is proportional to the area of the chip. Because you have transistors all over here, but the number of connections to the outside world is proportional to the perimeter of the chip. Because you're basically making connections only to the edges of the chip. So this creates a situation where there's so-called, a lot of times you are in a situation called being pad limited. So this could mean one of two things. Either that you always have fewer pads, fewer connections that you'd like to connect to the outside world. You don't have an infinite number of connections you can connect to the outside world. Otherwise, you'd have to make your chip very, very large. So you have basically those two options. If you never want to have a case where you have empty space on your chip because you needed to have pads there. So in other words, usually what pad limited means is that you have given all the functionality on the chip, you have a very limited number of connections. By very limited, again, means that, if you have a large package like this, limited might mean something like 300-400 pads, but it could mean as something as little as, 14, 44 pads, something like that. Are you guys still with me? Hopefully, seems like
Yes.
you are. Okay. So, okay, so we have these pads. Okay, so that's one thing. So let me talk a little bit about those in detail. So you have these wire bonds. Let me see if I have another better drawing of it. I guess I don't. So let me just draw a side drawing. Okay, so basically what this looks like is, if I look at the side of one of these wire bonds, I look like, I have the chip. Chip goes on. So just to give, I'll try to make it so it's almost to scale here. So the chip, let's say, is 700 microns thick. Okay, so it's glued on to the package. And then there is a cavity sitting here. So there's a pad that might be, excuse me. That might be 100 micrometers. I guess this is already not to scale. Sorry, guys, let me make this pad smaller. Make it slightly to scale. So this guy might be, 100 micrometers wide. And there might be a space of, the next pad over. Might also be 100 microns, 100 micrometers away. Now, why do we need, so like, when we're talking about stuff inside the chip, so when you're looking inside the chip, we're talking about transistor dimensions being, 14 nanometer, not microns, right? We're talking about, 45 nanometer. Nano is 10 to the minus 9. Micron is 10 to the minus 6. So there's like a order of magnitude, so sorry, 3 orders of magnitude difference, maybe not quite, right? Because we're talking about like double-digit nanometers, but let's say 2 orders of magnitude difference between sizes of stuff on chip and these dimensions I'm talking to you guys over here. And the problem is, what I described is that you're going from a stuff that you do on a chip to stuff that happens off the chip. So anything that happens off the chip, progressively the physical sizes get bigger and bigger. So this thing that puts, as I mentioned, something comes in and puts a gold wire bond, pad here is a little bigger, this gold wire bond between these 2 points. So that's not something that's made in a semiconductor process. That's like a physical thing that jumps between, the pin, the top of the tip of this wire bonding tool. So this is so-called a wire bond. It's made out of gold typically. So when you guys hear that gold is used as in the semiconductor business, it's typically in the packaging. So it might be, I'm going to put this on the screen. I'm using a fine tip for my iPad pen. If you guys see the pen I'm using to write my iPad, it kind of gives you an idea about the tip size of this thing that's going through and putting these wire bonds between the chip and the package. So physically, we're talking about already, even though this tip is fairly narrow, it's not something that's like in the 14 nanometer thing. It's, a fraction of a millimeter. So that's why these sizes immediately, are talking about going to larger sizes. So that's the thing that kind of happens between the inside of the chip, if you want to think about the package and the periphery. Things start going, like dimensions all of a sudden start getting big. And the other thing that happens is these dimensions don't really shrink like every couple of years. They're, if you look at the size of the opening needed for the wire bonds 10 years ago, and now it's about the same. Separation, it's about the same, because we're talking about mechanical things that don't advance at the same rate as silicon processes. So basically you're going from, putting more and more dense stuff in here with the number of connections to the external world not changing a lot, unfortunately. Okay, so that kind of keeps you in this pin limited world. So the other thing that happens is that if you think of this wire bond, it's this wire that's sitting, it's really sitting in, it's really hanging out in the air there. So the tool comes down, works with vibration, heats the tip of the gold. The thing is vibrating. It heats up the tip of the gold melts and connects to this pad. And then it basically stretches the line, goes here, and does the same over here. And it sort of you get two molten things here and here, and then it cuts off the wire. So this is really physically a gold wire hanging in open space. Okay, this is just the open, they close this up eventually, but this is just sitting in open air. So, or it's not sitting on top of anything. It's not sitting on a ground plane. Is that by that I mean? So, and also physically, this thing is, if you look at the length of this thing overall, the length may be 1 to 2 millimeters long. The width may be, the width is also about 100, maybe 50 to 100 micrometers. So if you can actually see it, if you look at the package, so I'm trying to think of what it would look like. It looks like a really, really fine hair, maybe. Maybe it might be a little thinner than a hair, maybe about the same width as a hair. But the upshot is something like this, classically, that's a wire standing by itself, etc. It means it has, all that it means it has a large inductance. So if you compare it to like a wire route on a chip, so let's say compared to a piece of metal on the chip. So piece of metal 1 through metal 9, say, okay. This has, as we saw, it has a large resistance because its thickness is less than a micron. Its width is probably less than, say, 10 micron for the sake of discussion. So you can see the cross-sectional area of this thing is pretty narrow compared to something that's 50 to 100 microns in cross-section. So this has low resistance, a wire bond. A on-chip connection relatively has large resistance compared to a wire bond. But this thing is sitting on a substrate not too far from a substrate, okay, meaning that its inductance is low, the on-chip connection. But then because it's sitting on a substrate, its capacitance is relatively high. And this guy is not sitting next to any other ground planes or anything. Everything's sort of far away. Everything is hundreds of microns or millimeters away. So it also has low capacitance. So a wire bond, you kind of have to, if you're going to model it, you'd model it as an inductor. Once you go here, there's capacitance because this is a fairly large plate. So this is a capacitance. And this is also could have a certain amount of capacitance, the pad. But the wire bond itself is really an inductor. Yeah, so that's the model. I don't know if you guys remember, but we said we tended to ignore the inductance on chip. So we basically only worried about, so on chip, sum total is on chip, only consider capacitance plus resistance, as you guys saw in your simulations. Project 3. In off-chip for wire bonds, we can essentially ignore resistance and we model it as basically an inductor. It might have capacitance associated with it, with the endpoints, again, because of the pads. And this inductance, as a rule of thumb, this is what's sort of typically used, is about 1 nanohenry per millimeter. of wire bond length. So a typical wire bond might have two, say, I don't know, 1, 2, 3 nanohenry of inductance. So what does that look like? If you looks like if you have a package, basically you have, what are the things you need coming in and out of a package? Well, you need signals coming in and going out. So, you know, you have some signal pads and some signal pins on your package. So they're going in and coming out. And so they have wire bonds, which have a certain series of inductance going in and going out. And then the second thing you have on your package is you have to have a way to provide power and ground to your chip. So those are also have some wire bond inductance. The resistance is like, you know, this shows some amount of resistance, but again, the resistance is fairly small. So really the main thing to worry about is the wire bond inductance. The other things, the other inductance that comes in, which, you know, this says is lead frame, is disconnection from this guy to, say, if you had a pin package, this connection is what's so-called the package lead. So this also has a certain inductance associated with it, with this so-called lead frame. In this case, you don't see this a lot, but in this case, they're using a decoupling capacitor on the chip, on the package, I'm sorry. So we'll talk about a little bit about this, but that's used to sort of decouple the power supply, but that also has some inductance. But the upshot is that you have inductance on your wire bonds coming and going. Okay, so if you have the way the inductors sort of add is what you want to do is, you know, inductors are kind of whereas capacitor resistors are, I guess, resistors, inductors, impedances. This is J omega L. Capacitance is 1 over J omega C. So if you want to have low inductance, you got to have multiple inductors in parallel. In parallel reduces inductance. So typically what you see, as this says, is you don't see a single wire bonds going to the chip package and ground, but you see multiple wire bonds going to them. So what people typically do is they connect up whatever they can in terms of the signals coming and going out of the package. And then the rest of it they use for power and ground, etc. So I'm going to jump over, I'm going to come back to the power, what do you call it? Power consumption, the power dissipation on a package. I'm going to stay with the inductance question. So basically you have this, what's so-called the package parasitic. So this is something you don't want, but you end up with. Okay, so again, why is this a problem? Well, it's because you have if you think of just your power and ground connections, so VDD and VSS, going to your package, going to your chip. Sorry. You can have a couple of different issues. You can have a problem with the total current. Or DC current. I shouldn't say total current. So you can have a problem with the DC current. And you have a problem with the AC current. So as you guys, again, hopefully remember, is that, if you have a chip, so this has, many, many gates in it, many billions of gates. Depending on whether if I use a CMOS inverter as a representative for these gates, you basically draw power from the power supply only when you're charging up a capacitor. So 0 to 1 transitions. Transitions give you a delta I on VDD. 1 to 0 transitions give you a delta I on ground or VSS. Okay, and you could end up with, every clock cycle, you might end up with, millions out of the billions of chips, even if only part of the chip is running, millions of transitions can happen every clock cycle. Meaning that you could end up with a large aggregate delta I. Sorry guys, my dogs are going nuts here. Let's see if it'll, okay, great, they quieted down. All right. No, they didn't. Let me go see if I can get them to stay quiet for a second. Sorry, I'll be right back. Okay, sorry guys. So I think that's the primary thing. Now there's this business of, so this delta I can be pretty large. And why do we care about that delta I? Well, again, I think we've talked about this a little bit, but if you look at an inductor with a delta I across it, the delta V is L di dt across this thing. And say this thing is your 1 volt VDD. And you want to know what this is. If this is a pretty big number, okay, this delta I. So delta I, think about delta I over delta T. Let me just say di dt. So this dt, the dangerous thing about this thing is this dt, like I mentioned, might be set by your clock rate. And think about how fast that is. If you have like a 2.5 gigahertz clock, let me do something that's easy to do the calculations on. Let's say you had a 2 gigahertz clock. That's a 500 picosecond clock period. And off of that, the rise fall times maybe, on the order of 100 picoseconds. And that's how fast this current is changing potentially, right? Because every rise fall time, there could be these changes. And again, remember, this is per gate, millions of gates, each one may be a few microamps, okay? But in aggregate, it could be, you're talking about many, many milliamps, or maybe, hopefully not amps, but many, many milliamps of change in current. But happening, this denominator is very small. So, if you imagine, I'm going to throw some numbers in here. Let's say if you have a nanohenry, we have 100 milliamps, and we have 100 picoseconds. What does that give us? So this is 1 times 10 to the minus 9. Right, so henries, that's amps, that's seconds. So this cancels with this. 9 and minus 3 are minus 12. So this is roughly a volt, which is your whole power supply. So if you had this situation where you had, 100 milliamps, just 100 milliamps of change in current in your sort of this rise and fall times, you would have your chip where the power supply, so out here, the power supply, instead of being 1 volt, it would be basically collapsed to 0. So this would be like a non-working chip, right? So this is the problem with this inductance. So what do you have to do? Well, you have to try to reduce this. We assumed the nanohenry. So that's like probably as small as you can get for a wire bond. You can't do much to reduce the length of that wire bond, but you could try to put in, so you could try, so how to solve this. You could try to put multiple wire bonds in parallel. Or you could put decoupling capacitors on chip. Okay, those are your two major methods of dealing with this thing. Okay, so so that's basically the issue you have. This is the problem with, as you can see, just like a nanohenry is not, for on chip, obviously it'd be a big inductance on chip, but off, like if you think about the inductance as like a number, it's not a very large number, a nanohenry of inductance. So it kind of shows you how big of a problem this is with this changes in current. If you actually have like the same situation, let's say if you had a DC current, of 100 milliamps. And you were looking at, so let resistance of say something on the package may be like 0.1 ohm or something. Okay, so if you have 100 milliamps, I times R of 0.1 ohms, maybe you're looking at whatever that is. It's just a 10 millivolt of voltage drop. So that's sort of a more of a, so this would be like a DC voltage drop, and this would be AC changes in the current. So the DC current drop is important. I mean, you don't want to give up 10 millivolts. And of course, instead of 0.1 ohm, it might be 1 ohm, or maybe it's 0.5 ohm, or maybe instead of 100 milliamps of DC current, you're talking about an amp of DC current. But you're looking at 10 millivolts, 100 millivolts, unless you really screw things up. The DC resistance isn't what's going to get you in a package with a silicon chip, typically. What typically gets you is the inductance and the AC current. Again, because of this DT that happens, it's very fast transitions. Okay, so what do you try to do to reduce that? Okay, so the main way to do that is by using bypass capacitors. So how does that work? So let's say you have a wire bond. So this is as a general idea. And this is your, say this is your chip. You basically put a bypass capacitor. You basically have these bypass capacitors everywhere. So let me give you guys a more realistic picture of bypassing. So this bypassing, by the way, if you guys learn nothing else in this class, basically this concept of using bypass capacitors is, let's see, why am I not seeing my, there we go. So this hopefully will be of use to you sort of in your microelectronics career, whether you're making chips or not, because you're always using bypass capacitors and any kind of a situation where you're using a chip on a package, etc. So you have basically, I'm focused on the package inductance, but really you have also inductances on your printed circuit board. So you can imagine if you had a board. So now, think of it as I don't know if you guys want to call it a motherboard or any kind of printed circuit board. You would have some kind of a connector on the edge of this where, it's either connected to your battery or connected to your power supply. In some way, power is coming in from some edge. And this is getting connected to a bunch of different chips, etc. And your chip is sitting somewhere over here. Well, this connection here from this point, so this is, let's for the sake of discussion, say this is, you have your clean VDD. This is some kind of a pristine supply voltage coming into your printed circuit board. So from your clean VDD, you would have some inductance, which would be the printed circuit board routing, would have a certain wire inductance. Then you have the wire bond going into the package. And then you'd have your chip. And then you do the same thing with the ground. So what you would do is at each point, I think we talked about a little bit about this, but we would try to put decoupling capacitors. So this would be, either on the package or on the chip. So if you actually look at a printed circuit board, you'll see them filled with like these decoupling capacitors. So I guess they would be going to this. And what's the idea behind this? You can think of these as, there's two ways to look at decoupling capacitors, which is somewhat, I guess it's really the same, but different, you see different graphs that convey them in different ways. So, but in either case, I guess the way I look at it is it's a charge reservoir that what happens is if you get a very large transition in current, so if you have a large delta I going through here, what this guy can do is it can provide momentarily for a real short amount of time. For, this guy might be, looking at 10 microfarads to 0.1 microfarad is what you'll typically see on a board. On a package, you also might see 0.1 microfarad. On a chip, you might see more like hundreds of picofarads of capacitance. So this has a certain amount of charge there, which is the total charge that stores on it as Q is equal to CV. So whatever that ends up being, so that with that capacitance and the voltage is the supply voltage, 1 volt, just sitting in. So it sort of charges up when there's no transition up to the supply. And let's say it gets hit with a delta I here, this guy will droop, but this guy supplies that momentarily current locally and bypasses this inductors. That's why it's called decoupling. Sometimes they call it bypass capacitors as well. So you're bypassing this inductance just for these delta I events, because as soon as you supply the current, that charge is gone, and then this guy tends to droop himself, and it needs to get resupplied from this current, okay, through the inductor, but at a slower rate, so there won't be as much droop. So let's say you have two ways to look at these bypass caps. You can look at them in the time domain. Or you can think about them as in the frequency domain. It's the same device, it's just how you look at it. Okay, so in the time domain, the idea is that if you have, if I draw it, this is time. Say if I have if I'm drawing a current, let's say this is a sort of a delta I event here. So this would be my chip drawing an excessive amount of current or a certain amount of current at a particular point in time. If I look at the voltage, so I'm going to draw, this is point X. So voltage at point X will start at 1 volt. When it gets hit by this, it'll droop. The capacitor is going to be basically providing this current. Okay, and then eventually, because this is just momentary and it goes back to a DC value, so it supplies that current and reduces your droop, and then eventually comes back up, because after this pulse comes and goes, then that inductor doesn't, from a circuit standpoint, the inductor doesn't exist anymore. And it looks like you're just connected to the supply again, and does your capacitor charges back up. So this is with decoupling. And without decoupling, what would possibly happen is this guy would collapse. Again, it would recover very quickly, but it won't do you any good. So the red would be without decoupling. So basically your chip would be completely fall apart here. It would recover. Actually, I should make it, make it more accurate here. So without decoupling, it was just really, if it was totally without decoupling, it would just follow the current, because it would only be, wouldn't have much of a droop. But so you'd have this momentary, without decoupling, you'd have this momentary complete collapse of your power supply going to the chip, which would be total disaster. Your chip would stop working. But then you'd recover quickly, but so what? Because your chip just totally went, just everything in your system fell apart. Or you basically use this decoupling capacitor to get a much lower droop in your supply, but it needs to get charged up. If you had events that kept just having current spike after current spike after current spike after current spike after current spike, then basically this capacitor wouldn't really be able to recover. So it would eventually droop down to zero as well, because eventually the capacitor is just going to run out of charge. It won't be able to get resupplied again. But you're basically, that's how you size the capacitors, is you try to figure out, what these droops, these current droops are, and try to sort of figure out the appropriate sizing for your capacitors. And I'll tell you about that a little bit more detail. The other way to look at the decoupling capacitor, so if you look at it from a frequency domain, if you look at it like that. So think of it as having an impedance of 1 over j omega c, right? If you look at the impedance of this capacitor. So as the frequency is low, this impedance is very high. So imagine in DC, when there is no change in the signal and zero frequency, this looks like an open circuit, right? In the AC domain. As the frequency increases, oops. As the frequency increases, this impedance drops lower and lower with higher frequencies. So what does that mean? Well, it means that the DC current that you want just goes straight through, doesn't notice that this guy's here, the DC current. The AC current that you're trying to get rid of, or those, well, actually, let me put it in terms of voltage. So the DC voltage that you want doesn't see anything here, right? So the DC voltage just goes straight through, okay? The AC voltage, which is this droop that you see, sees this as a short to ground, okay? So basically anything that, any big changes here get basically shorted out and disappear, ideally, and only DC signals pass straight through. So it's kind of like having, well, it's not kind of, it is, it's basically a low pass filter. Okay, so if you just look at the impedance of a capacitor in the frequency domain, it's gonna look like just a capacitor. it's gonna look like it'll have some kind of an impedance like this. So if your voltage glitches are really high in frequencies, I mean, something like 100 picosecond rise time is going to have really high frequencies associated with it. Okay. Then basically all those frequencies are sitting out here in high frequencies. So they just see a short, like your chip won't see those. It's like trying to pass a high frequency signal through those. It won't really pass. So it's only going to let DC voltages through or relatively low frequency signals through. So that's the AC way of looking at that decoupling capacitor. Now, unfortunately, in a real capacitor, a real decoupling capacitor, so this is part of the way you have sizing on chip. If you're looking at an actual capacitor that you would have on chip, surface mount capacitors, on printed circuit boards, they might be like maybe several millimeters in size. And they might range. I think the one I've seen on the sort of the big size typically is maybe 10 microfarad. That tends to be, that's a pretty big boy. That might be maybe 5 by 5 millimeters or something in size. You see that size, you see 1 microfarads, 1.1 microfarads. These are typically sizes you see, and then gradually get smaller and smaller. This might be a millimeter by millimeter or something like that. Okay, so each one, why am I mentioning the sizes to you guys? These are sort of biggish devices. And what happens is, instead of these surface mount capacitors, so ideally this is what you think you're buying. What you're really getting is some kind of the capacitor itself has an inductance associated with it, because there's a physical size to this capacitor, and it's also getting connected up to the printed circuit board. So if you look at, so this would be sort of an ideal capacitor frequency response. The real capacitor frequency response would kind of look like, would end up having some kind of a thing like this. So real capacitor. And what's happening there? Well, this is 1 over j omega c in terms of impedance, but the inductor, so this is the self-inductance of the capacitor. So this is the capacitor's inductance, not the board inductance now. So this is sitting sort of in series with the capacitor, and that's j omega L. So that's going up sort of with frequency. The capacitor is going down in frequency. So if you look at the operating frequency, like the useful operating frequency of a real capacitor, it's somewhat limited. This means that if I'm drawing this means that this capacitor is good at getting rid of glitches kind of in this frequency range. Okay, so by the way, let me talk a little bit about, so what does this mean in practice? Let me just sort of jump ahead and say, so what you do is, this is why people use this is why people use different capacitor values. So, a 10 microfarad capacitor has a different combination. It has like a higher inductance than 1 microfarad capacitor. So it's going to have, high capacitance. So it drops. If I just look at this as the frequency response of a 10 microfarad capacitor, it's going to drop, and then it's going to start picking up at some point. So if you put that in parallel with a 1 microfarad capacitor, the 1 microfarad capacitor has lower inductance. It's physically smaller. So it's going to start, because but it has lower capacitance. So it's going to have a frequency response that goes down sort of later, but then it comes up later as well. And then this one may be a 0.1 microfarad capacitor. So it says a 0.1 microfarad capacitor. So what you end up doing is to try to get as much low impedance points as possible, as a range to increase your low impedance range of frequencies. You basically are putting in a bunch of different value capacitors in parallel on the same signal. And that's why you see that, you're using these capacitors. If you look at like the printed circuit board schematics, etc., you'll see this a lot. You'll see different value capacitors sitting on, basically decoupling the same line, the same power lines. Okay, so for example, well, let me talk a little bit about that. Do you guys have any questions about that so far? No? Okay,
No.
so go ahead. No? All right, so let me talk a little bit about, just take a quick, so I think hopefully this stuff makes sense to you guys, but let me just take a little bit aside about, I think this is pretty obvious, but I want to mention it anyway. So, when you're looking at time response, so now I'm talking about the frequency response. Now, the question can come up about, we're looking at a digital circuit. We're not looking at an analog circuit. Digital circuits have rise and fall times. So they have clock periods. They have rise, fall times. So, when you're working on a digital system, this is the kind of stuff you see, right? So there's a, clock period. There is, rise and fall time. So you don't hear, I mean, maybe you'll hear clock frequency, but that's really just one over the period. So to me, at least, it's more intuitive when you're talking about a clock, sort of a digital system, sorry, to think about the time domain, right? So you're thinking in terms of this, to me, this makes sense, right? You're operating in the time domain. I've got time drawn in this axis. And, so, I'd see a glitch in time. Okay, there was like some kind of a rise or fall time events, or a bunch of rise and fall time events happening here. And I can, like, that makes sense. How do I get this? How do I end up in the frequency domain? So what happens is if you look at a square wave in time, you can take the Fourier transform of this thing. To look at it in the frequency domain. Okay, and what you'll see, I won't get into this very much. You guys can kind of see this in different books on, probably, where would you see it? I think it's sort of mostly in digital communication classes, etc. What you'll see in the frequency response is some kind of a thing like this. Okay, so at different frequencies. So basically when you have, another way to look at it is if you had to get a sort of a fast square wave here, you would need, you could do it, this is a frequency transform or, sorry, a Fourier transform, but you could also think about this as being a combination of Fourier series of different sine waves added together at different frequencies. So long story short, to like something like a sharp square edge like this has a bunch of frequency components, in the frequency space. If you look at, if you put a spectrum analyzer on this thing, or if you do a Fourier transform on a square wave, they'll have like a bunch of frequency components. And the faster this edge, or this edge, depending on which ones you're looking at, the more sort of the more of these frequencies are at like higher frequencies. So it's not a direct correlation between the rise and fall times, and frequency domain, but basically the faster, the shorter rise and fall times, the higher the high frequency components are of a transition. Although this has many different frequency components. And you're trying to basically, with this decoupling caps, you're trying to get rid of as many as you can that are not DC. You'd ideally, you would like to get rid of anything other than DC. Like if I was going to have a decoupling cap, that would be perfect. I would want it to be something like this, going to zero or below zero. And, in terms of impedance, I'd like it to be very low. But basically you can't with realistic capacitors, and you basically try to get as many of these dips or low impedance points as you can to try to squash as many of these frequency components as you can. Okay, so if you look at like sort of papers, I think on what this looks like. Okay, so you see either stuff based on the time domain or the frequency domain. So for example, these are from a couple of different papers. Think first about this one. Okay, so this one is, you got the time domain and you're looking at the supply voltage and the effects of, different things kicking in at different places. So for example, if this doesn't quite, you guys can't quite see this, but in this thing, so what it does is try to draw over it. So come here, you get a glitch, it goes all the way down, comes back up. It's that's what it looks like. You can see the rest of it. So what happens is this first droop is basically, it's so fast, such a fast edge that the only thing that can respond to this is really the same droop. Okay, this is the same event that these different capacitors are responding to. Okay, so you have these different capacitors that are responding to the same event. So the first thing that responds to it, that can respond to a fast droop, is the on-chip. So these are the on-chip bypass caps. So those are sitting sort of out here at the higher frequencies. So this is on-chip bypass caps, highest frequency response, but lowest value. Okay, so what does that mean, lowest value? Well, you can't get a huge amount of capacitance on chip. So this guy gets a pretty high droop because the capacitor runs out of charge really fast, right? But thankfully, it seems to like keep you start at 1.2 volts something, then droops down below 1 volt, but then recovers. So but it's the only thing that can respond. So there's also the package and board capacitances. So you can see this the package decoupling capacitors might be sort of this intermediate frequency. So it responds later. So it's not able to respond at this speed to the droop event, but it responds a little bit later. And sort of starting to kind of recover over here. And then lastly, the board capacitance is out here. So you can see that's kind of like the third droop that it's hitting. So basically, you're relying on these different decoupling capacitors starting to kick in and provide the current. So this is the board, sorry, the chip cap. It gets charged up by this time the package decoupling cap is starting to like respond. So the package decoupling cap sort of charges it back up. And then by around this much, like the board capacitor kicks off to, get it to recover. Okay, so you can kind of see how these things look on sort of a real-time domain response. So the things to look at here is one, how fast these events are. You can see how sharp this was. This is, microseconds. It's still a pretty long time, but very, very short transition that it tries to respond to. And then how slow these capacitors then start to charge back up, because you got to basically charge this reservoir, very large capacitive reservoir back up. Okay, so the other way to look at this is from a different paper, but it kind of gives you what these multiple impedances look like in the frequency domain, and how you have different things that are trying to kick in at the same places. So you basically have this board or this chip had some kind of a target impedance value. So you wanted it to have a very low impedance. So if you had these inductors and stuff, you wanted the impedance of this thing over the frequency space to be low. I know it's like a milliohm across. That was the goal. And you see in reality, you basically have these series inductances that sort of cause this peaking of, you got at the package happens at higher frequencies, and then at sort of lower frequencies, you get different things are peaking. Okay, so that has to do with the inductance of the package. Okay, let's see. Okay, all right, guys. So this is what, as you'll see, what we're going to do is basically have you're on project 4. We're going to add basically this. So what you had for project 4, again, you had this modeling of the load for clock. And then we're going to add the inductance of the wire bonds. For the supply and ground. And then we're going to look at how you can basically, I'd have to sort of, let me draw. You could try to basically decouple, use decoupling, like what type of decoupling you'd need to try to get rid of that or reduce it to something reasonable. Okay, so that's the wire bonding inductance. there's one more thing that I wanted to talk to you guys about, which is how to drive this guy. Okay, so this guy, as I mentioned, going back, so this was first topic, right, in terms of dealing with the outside world, which was back to, let's see, what was I talking about? No. No, was I talking about it here? Well, let me talk about it. Same graph. So that's sort of one issue, which is how to so basically what type of decoupling. Okay, so then the next thing is how do we drive this large capacitance? Because, I think about like your devices, I'm gonna guess, let's see. Let's say we might have, like, let's say the total capacitance you guys were driving and total resistance. Capacitance might have been a picofarad and the total resistance might have been kilo. I don't quite remember what it was, but something like that as this load. This driver itself might represent, 200 femtofarads or something like that to something else driving it. And remember that the smallest, so this was, I don't know what you guys were using, but I think I was using NMOS of 80 micron with maybe, and PMOS of maybe 200 or 160 micron width, something like that. Remember that the minimum size device that you can get in this process is maybe 1 micron width. And so you might be in a situation where there's some computation happening. You have maybe a minimum size device that is the output of that block. And then that guy somehow has to drive this guy, which might end up being too much for it to do directly. So what you end up doing when you have to drive a large load, typically, so this is your project 3 inverter. And let's say you want to start with a minimum size inverter. I'm going to draw that really small. There's a bunch of math involved there, but basically what you end up doing is you go to subsequently larger and larger. You don't try to, it's inefficient or very slow to try to drive this guy directly with this guy, with the small size. So driving this guy directly with this guy is way too slow. So what you do is you will go to progressively larger and larger size inverters, and this ends up being more speed efficient, although it might be more like less power efficient than this thing, but it's more a speed efficient. And this multiplicative factor is approximately 3x for each stage. So how does that work? Let's say this is 80 micron NMOS. You try to drive that by something 3 times smaller. So let's say that, doesn't quite exactly work out. Let's say that's a 25 micron NMOS for this subsequent or the previous stage. And then you go another stage that's 3 times smaller than that. That is, I don't know, like maybe 8 micron wide NMOS. Then you go to another stage that might be now 2 microns or so wide, which is getting close to a minimum size. So you end up basically needing to put in a couple of extra stages in between to drive a big load on chip. And so that's the second thing. So if you have a small driver going to a big load, that's what we'll be looking at in the project, how to do that and what that means in terms of speed and power consumption. Okay, guys, I think I'll stop there. Any questions?
When will you post the project 3 to Canvas?
I'm sorry?
When will you post the project 4 to Canvas?
So I'm gonna put project 4 on campus by Monday.
Okay, and then do next Saturday? Or
Yeah, I think I'm gonna make it due also on May like 22nd, whatever, like the Monday
Okay.
after the final. So you guys kind of can try to take a breather with or I don't know if it helps or hurts you guys, but yeah, it'll be basically due at the end of the class. Any other questions, guys? Okay, have a good weekend, guys. Take care.
Professor.
Bye. Let's see. Is it Alex?
Yeah, I emailed you. It was basically just I turned in project 3. So I was out of town all weekend. So I turned it into you last Friday over email. I never read on Canvas to turn it in.
Yeah.
And then I noticed, because I haven't been on like for your class on Canvas till today. I noticed that announcement. So I tried to resubmit it today, but the link was closed. So I sent you another email about it. And I was hoping, because I remember in the beginning of the year, you talked about there's like one of our projects we could turn in up to a week late and receive
Right.
the same grade. If I could
Yeah.
just, hopefully this one would count as that.
Yeah, I think you can do that. So what I'll do is I'll open up the canvas for you right now. And like,
Okay.
we can turn it in by noon tomorrow, or whatever.
Okay, sounds good.
Yeah.
Thank you.
Okay. Sounds good. Anything else, guys? Okay, I'll let you go. Take care. Bye.